have today a seminar on quantum science by Yue Ban. So Yue, so she did her studies on physics in Shanghai, if I am correct. After that, she did a PhD at the University of the Basque Country in Bilbao with Professor Sherman. And since then, she's been working at different groups. She's currently also in Bilbao and working with the group of Enrique Solano. And today she's going to be talking about the methods and applications of quantum control. So you're all yours.
Okay, thank you very much. My name is Yue Ban. Now currently I'm working in the Department of Physical Chemistry, University of the Basque Country. Today I feel very glad to give a seminar about methods and applications of quantum control. We all know that modern quantum technologies come in different forms like quantum computing, quantum simulation, quantum sensing. But all of these, there is a very important question that is how to precisely and fast control the physical systems. So today I will introduce you some methods that we recently used, like shortcuts to adiabaticity, some methods of machine learning, neural networks, reinforcement learning, deep reinforcement learning. And using these techniques, I will show you these results, the progress that we have achieved recently about fast and robust spin control, qubit control, neural networks to do the parameter estimation. And we also incorporate shortcuts to adiabaticity to do the speeding up quantum perceptrons. And finally, I will give a general perspective. So we all know that adiabatic passage is widely invoked in many different systems due to its robustness versus deviations from ideal parameters. However, this adiabatic passage takes typically quite a long time. So the system could be prone to noise and decoherence. So people always ask how to speed up this adiabatic passage, but achieve the same results from the adiabatic process. So this technique, shortcuts to adiabaticity, can solve this problem. Well, this technique was firstly put forward in more than 10 years ago. So the first paper, this concept was put forward in this paper, and it was down to speed up the atom cooling. And after this work, this technique has been applied in different fields. And now it becomes an important tool in quantum control. So you can refer to these two review articles. So there are many techniques of shortcuts to adiabaticity. Like firstly, inverse engineering. This technique, suppose you know the initial state and the target state that you want to achieve, then you can inversely design the Hamiltonian. And second one is transitionless quantum driving, or we also call this counter-diabatic driving. This one you can use it to find the counter-diabatic term so that the state evolution is always along the instantaneous eigenstate of the reference Hamiltonian. And also there are many other methods like fast forward scaling. Now, recently, this method has been used in 3-level nonlinear system. And also other methods like rapid scan approach, like SPARE. Also, we can combine with flow-get engineering or optimal control theory to do the shortcuts. And also here, I want to mention that this technique has been verified in different quantum systems experimentally. So here I show you these experiments in 2-level, 3-level quantum systems in optic lattice, in solid state like NV center spin and transmol circuit, superconducting qubit, X-small qubit cold atoms. Well, for me, I have been used this technique since years, especially in the quantum dot systems, because this system is easy to fabricate and very easy to engineer the quantized energy levels. So I have used shortcuts to design the protocols for non-adiabatic charge or spin state control, including the single spin qubit with spin orbit coupling and singlet triplet qubit in a double quantum dot, or 2 interaction spins and charge transfer in long-range quantum arrays. And also we can transfer the entangled spin state like singlet triplet in an arbitrary long quantum dot array theoretically. So here I have done many works. These are the only several works for the time limited I show you here. Also, I have also used shortcuts to adiabaticity in different systems, like photon polarization rotator and spin orbit coupled cold atoms in Morse potential, and also the spin control of spin orbit coupled BCs in moving harmonic traps. I think the results of this article are also applicable for electron transfer by surface acoustic waves. Okay, since 2019, I came back to Bilbao. My colleagues and I have developed different hybrid shortcuts to adiabaticity techniques, combining with other methods. And I have also extended my research scope into like quantum sensing, machine learning, quantum machine learning. Here, I show you this the cooperation between shortcuts into and optimal control theory. Then we can achieve the time optimal control of nonlinear 2-level system and achieve the quantum speed limit. And we also incorporate the shortcuts into dynamical decoupling in a quantum sensor. And we can achieve very high fidelity with respect to the systematic errors. Also, we combine shortcuts in deep reinforcement learning. And this deep reinforcement learning can help to design the digitized pulses for qubit control. And we also can use quantum, this neural network in quantum sensing to do the parameter estimation. And we also can do shortcuts in to design the quantum neural network. Here, this article also shows that shortcuts can speed up quantum perceptrons. Okay, then after this brief introduction, I will show you some results. Firstly, this is very general, the introduction of the spin flip of a 2-level system. Then we can see that a spin can be represented as parameterized by 2 angles on the Bloch sphere. They are the polar angle and azimuthal angle. And this equation of motion can give the mean value of the spin and give the dynamics of the spin. So then we can get these theta dot and phi dot, the dynamic equations. These 2 equations actually can be obtained by dynamical invariant. Also, it can be solved by a Schrodinger equation. And then remember that we want to flip the spin, then we just set the boundary conditions initially and finally, and get some or set some necessary conditions there. Then we can use the above two differential equation. Then we can inversely get the external field that we want to design. Okay, that is the general idea. Then we design this technique in the Hamiltonian for Landau type. This is quite typical in superconducting transmor qubits, BECs in optic lattice or quantum dots. Especially, I think in quantum dots, for example, one electron is in a double quantum dot. Then this tunneling between the dots always is a constant. So we just change the tuning of these two levels, and then we can control the state. And we just parameterize this Lewis Rosenfeld invariant and get these two dynamical equations, zeta and beta. Also, this gamma is the Lewis Rosenfeld phases. They are related to these two angles. And then inversely, you can get this detuning equation. So here, maybe we can just set a polynomial answers for this zeta to connect the initial and final conditions. But apart from polynomial answers, there are many other optimal protocols to cancel the systematic errors. So here I show you. Firstly, we set the boundary conditions initially and finally, and set the time derivative at these 2 points, just because we want to have the smooth control. And then we can get another important boundary conditions. If this condition is 0, this means that we can cancel the influence from systematic errors in the transition. And then here I show you this result. This zeta is set not only in a very ordinary polynomial answers, but also we introduce some undetermined parameter, this A. So according to your requirement, like if you want to cancel the errors in the Rabi term or in the detuning term, then you can find the optimal choice for this A. Also, we can find also simultaneously to cancel both of these two errors. It's impossible. It's possible. And the other one is this deep reinforcement learning. Why we use deep reinforcement learning? Just because from shortcuts to adiabaticity, we can design the continuous protocol for detuning. But for experimentalists, maybe they want to use the limited steps of pulses. So these pulses maybe has some just n steps. So how can we do this? Then this deep reinforcement learning can help us. Here, the agent is the deep artificial neural network, and the input layer are the encoded states. And after this neural network process, then we can get the encoded action. This is the tuning in the next time step. And then we can say that this deep reinforcement learning can obtain the digital shortcut pulses. Actually, here, shortcuts educated deep reinforcement learning agent gives the bound operation of the operation time. But this deep reinforcement learning explores protocols independently. So these are the results. These are the theoretical results of the detuning pulses. with respect to different errors in theta and omega. And we see that these shortcuts, both shortcuts and deep reinforcement learning, can give higher fidelity compared to pi-positive. Also, our results has been verified by an experiment recently. And this experiment uses the system of ytterbium ion system. And then actually this experiment demonstrates that this deep reinforcement learning can give very high fidelity against Rabi and the detuning errors simultaneously. And without, this is done without the input from shortcuts. Okay, this is for the qubit control. Then we also use shortcuts combining with dynamical decoupling to design the pulses in quantum sensor. Here, it's very similar to the previous case, but we also use the boundary conditions that we want to achieve. And also we cancel the errors and eliminates the control errors. And we also use very important condition here. This is the maximum NV target interaction strength. And then we can achieve very high fidelity qubit control compared to the pi-pulse sequences. Okay, this is the first part. Then I also have done something like neural networks for parameter estimation. Well, neural networks actually bridge the input data into output results by approximating the function that relates them. So actually, this quantum sensing is just a natural playground to show that neural network is very useful. Here, this input data is the response of the system when you apply the external field, and the output can be the estimated parameters of your applied external field. So here we just show one example. This is also ytterbium atomic sensor. If we shine external electrical magnetic field in the form of omega cosine small omega, and this field can be detected by using 0 and 1 state transition. In the past, if this response is in the harmonic form, this is like this red line, then we can estimate the amplitude, this amplitude, the capital omega of the field. But how can we do when the working regime is beyond this harmonic response? This means at this time, the rotating wave approximation is not valid. How can we estimate this the parameter of the external field? Then I think a neural network can do this. We just set the neural network. The input is the measured data. This is the sensor response that I mentioned. Here, this is the state probability at different time, and the output is given from the neural network, and the target is the amplitude of the external field and the tuning. So in order to achieve this fx, this is the action from the neural network on the input x. So we have to establish a training data set training data set, and with the tolerated error, that we can say that we can get very high fidelity output of the estimation parameters. So we use the standard stochastic gradient descent, and update these bias and weights of the neural network. Here, I want to show you that the output is very, very close to the targets. So these two lines coincide. Here, because there are, this is the ideal case, I didn't consider any noise here. So the neural net works so perfect. But what if we consider the situations with a significant short noise? So theoretically, we numerically simulate experimental acquisition to include short noise. But here, I want to say that actually in experiments, without, if you don't know the physical model, it doesn't matter, because the data just comes from the experimental measurement. So here I simulate this data for every time measure 100 shots, and because of this short noise, the results are different. So I repeat 20 times for each of the experimental acquisition, and we find that because at some regime, very wide regime, omega TG from 1 to 25, you can see that the deviation between output and the targeted is very large. But if you decrease this regime, then you will get very high fidelity. This is just because at small omega TG, these two signals are not easy to identify, but at small time. But if you increase this omega TG, then you will find they are very easy to be distinguished. So we choose this working regime, this one, and we can get the results that, well, the fidelity or the accuracy of our neural network is above 97%. So this means that using the neural network, you can have very little pre-knowledge of the physical system. And also another advantage is that after you fix the working regime, then you just send the signal into the neural network, and you will get the output very fast. So compared to other like a Bayesian estimation, this is the advantage that we use neural network. Okay, this is the part for the neural network. And also I want to mention that we also use shortcuts to speed up the quantum perceptrons. Well, the emergence between the quantum computing and the artificial intelligence nowadays has boosted the development of both fields. So the quantum neural network is a very good example. So the neuromorphic quantum computing can offer the advantage that like quantum superposition, quantum parallelism, quantum entanglement to speed up the operation of the neural network. So I just give a brief introduction on this quantum neural network. It was developed since 1995. And after this seminal idea, many different kinds of models have been introduced, like continuous variable quantum neural networks. Here, I want to show you briefly about these two these two models. One is repeat until success technique for quantum gates. This perceptron uses the concept of repeat until success technique. So if you measure this ancilla qubit, if the result is 0 state, this means a rotation along the sigmoid transformation is already done, and then you can get the output qubit. But if you measure this ancilla qubit is like state 1, then this means this is not okay. Then this circuit will repeat until your 0 state is measured here. So this is called a repeat until success technique. And the other one is sigmoid response function in a qubit with quasi-adiabatic process, this transformation. And this unitary transformation works on a qubit. The initial state is 0 state. Then at some time, after the operation time, then you will measure this state. So the probability of the excited state versus the input neural potential will give you a sigmoid-like activation function. So this here, this neural potential is the weighted sum of the neurons in the previous layer. And this unitary transformation can also be dynamically engineered by this Hamiltonian, which is in a standard Ising model. Okay, then this Ising Hamiltonian has the reduced eigenstate. This is the reduced eigenstate. And this Fx has the, if the system evolves in adiabatic way, then this transfer function is in a sigmoid form. So we want to speed up this quantum perceptron in a non-adiabatic way. So because if it takes long time, then it's very prone to the decoherence. So how to speed up this? Well, so I list these two routines. Firstly, we use the hard-mod gate from 0 state to plus state, and then we design by using shortcuts to design this omega t from plus state to the state of this eigenstate at the final time. And to do this, we use the inverse engineering. Also, this is the standard way. Then we parameterize the state on the Bloch sphere by means of these two angles. And we can inversely get the external field omega t. Well, I have to emphasize that this activation function should satisfy the following conditions. One is that this function should be monovalue, and this universality of the perceptron does not rely on the specific shape of sigmoid function. This can be more linear or more nonlinear. So just they are in the shape of sigmoid function, it's okay. And then the control should be also independent of the input field. And now we use this function, define this function, to see whether our construction of perceptron is successful. This C. This means that whether at some point minus x marks, like here, this is going to very approaching the 0 state, and at some x marks at this point, our state is approaching this 1 state. So we can see that using our inverse engineering, actually we can construct this sigmoid-like activation function this is successful. Besides this, our designed omega t is more easily to be implemented compared to this quasi-adiabatic protocol, this red line. And also, our method provides a wide range of input potential compared to the adiabatic or quasi-adiabatic process, because we have a wider range of lower C. And most importantly, our protocols is successful to provide a quasi-time optimal solution. This means that here, this red line is for the Faquat. This is the fast quasi-adiabatic protocol, and it gives the minimal time of operation like 0.3. Then our protocol can shorten this operation time by a factor of 2. And not only of this, because of this, but also we can see that our method is robust with respect to timing errors. We are here we are more stable. And now I also want to emphasize that we have proposed the application platform ME centers, like at the room temperature, the TF should be like 75 nanosecond, and the coherence time is much longer than this time, so the coherence is quite well preserved. And also this inverse engineering, this method is helpful to achieve when one considers this easy model with unwanted transitions. Okay, these are the main results that I have shown you that we have achieved. And finally, I will give you some my personal perspective. Firstly, I think we can continue to do some faster and robust spin qubit control by combining shortcuts with other different methods like dynamical decoupling, deep reinforcement learning, variational methods to control the many-body systems, especially like I think the local counter-diabatic driving is quite useful. And also we can use different optimal protocols to approaching the target, like different optimal motivations. For example, in the quantum dots, how can we reduce the charge noise, the influence from the charge noise? Then we can use maybe reinforcement learning to do it. And also, because shortcuts was derived, I think in the regime that rotating wave approximation is valid. So how about the strong applied field is used there? So how can we achieve these strong fields with high, the protocol with strong fields with high frequency? So we can combine shortcuts with Floquet theory and get local counter-diabatic driving. This is for qubit control. And the other one is that I think this is here I show you these shortcuts to adiabaticity in digitized adiabatic quantum computing. This is the work done by colleagues, and they use these shortcuts to simulate adiabatic quantum computing by doing some state preparation. Why we want to do this quantum algorithm by using shortcuts? Because we think that there exist some similarities between shortcuts and some quantum algorithms like QAOA, because QAOA uses the framework of the hybrid quantum classical algorithm to solve the configuration of the problem Hamiltonian at low energy. similarly, shortcuts shorten the operation time, but simultaneously minimizes the energy excitations at the final time. So they have very much similarities in the motivation. And I think the cooperation of these shortcuts into QAOA can really enhance the performance of QAOA. And also, after this paper was published, or at the same time, almost at the same time, these two articles were published in very similar topics. Especially this paper also used the counter-diabatic driving for stated preparation by using some reinforcement learning. And then I think if we use shortcuts, we can speed up quantum algorithms to do some very practical problems like Marx-Cart 3-set problems. And for the application of graph theory, financial market logistics. And also, we have also done some work on the VQE in state preparations. Then I think we can simulate the molecular dynamics in quantum circuits, and then using shortcuts and other different optimal theory to speed up, optimize the molecular dynamics. And last but not least, that we will continue to do neuromorphic quantum computing. In the previous introduction that I show you the results here, we just use the qubit. They are very standard EC model, which is the 2-qubit interaction. But if we include more interaction from different qubits, then how will the neural network become? Actually, we have already seen some simplification of the introduction of these multi-qubit gates. And it will really decrease the layers and the numbers of neurons to do some logic gates compared to the classical neural network. And also, if we achieve the optimized QAOA algorithm, I think this is quite useful to training the quantum neural network. Okay, these are my main collaborators. Thank them, and thank you for your attention. If you have any questions, we can have further discussion.
Hey, thanks a lot, Yue, for this very nice talk. Yeah, let's see. Are there any questions? So if somebody has any question, I don't know if I have to unmute you or you can directly talk. So feel free to turn on your microphone and ask a question. Otherwise, I have some question actually. So when you were talking about neural networks and deep learning, you didn't offer too many details about the neural networks themselves. So how was the training time of the networks, and also how deep was the neural network? Did you have different layers or just one? Or
okay, this is the deeper reinforcement learning. So we have 3 hidden layers, and the inputs have some elements like the element of the density matrix and the detuning level at the previous time instant. And after this processing, we will get their output. This is the detuning at the next time instant. And then we put it into the environment, that is to put the Liouville von Neumann equation to see finally at the final time this fidelity is above the criteria that we set. If it's successful, then we will get some very good reward. And the time of this deep reinforcement learning, we just set is as bounded by the shortcuts.
You also mentioned you use a stochastic gradient descent for training the network. So for training the networks, I think at some point you mentioned that you use a stochastic gradient descent.
Ah, yes.
So did you try some other algorithm, or?
You mean this?
Exactly here.
Okay, here so far we just tried this stochastic gradient.
Okay.
Test. Yeah.
I have also well, I don't know, questions from the audience. Okay. I have actually another question. So when you were talking about quantum neural networks, and this is maybe yeah, I mean, this is something that maybe you could clarify me. What's actually the difference between a quantum neural network and a variational quantum circuit? Because to me, it looks like, you know, a variational quantum circuit is already the quantum version of a neural network, no? So
yeah, I think variational is a form of quantum neural network. Yeah, it's like in a quantum circuit, you will have the specific physical form. Yeah.
Yeah. So all these models of quantum perceptron and so on, this is nothing but a specific case of a variational quantum circuit, no?
Yeah, you can understand in this way. Yeah.
All right. Good.
I think
more questions. Yeah. More questions or comments or remarks from the audience. Oh, I see that there are in the chat there is something. Gesa. Gesa, Kitske, I don't know if I can permitir hablar. Yeah, I think Gesa, now you can talk.
Yes, I think. Thank you. So, you hear me?
Yeah.
Okay, thanks for the talk. I had a question concerning this whole field of shortcuts, Adiabaticity and quantum control to mitigate or avoid errors. And my question was, what are you kind of considering a fixed, let's say, noise or depolarizing channel or something acting on the qubit, and then you modify the Hamiltonian? Because I think it seems the Hamiltonian can be modified in quite sort of strong ways, which might in itself affect what kind of noise the qubit feels. So I was wondering, when you compare how much better a system is controlled, or how much noise it avoids, what is the underlying model for describing the noise, and also is the Hamiltonian that you apply for doing the control, is it considered to be perfectly implemented, or do you include imperfections in application of the control Hamiltonian?
Okay. Here, this qubit, when I talk about this qubit control, actually in these two works, we consider different deviation from, we consider different deviation from this detuning, deviation from this Rabi-term. They are in this form. Then we can find this is the results that we calculate from the perturbation theory. Then if this term is 0, then we can say that we can cancel the deviation, the influence from the deviation. This is one respect. The other respect is that we also consider in the master equation, maybe not in this work, in the master equation, that we consider some white noise or more complicated noise, and to see whether our protocol is robust against them.
Okay, and this is you have kind of a fixed rate with which, let's say, the noise is injected into the system, and then on that background you are modifying the Hamiltonian in order to reduce the
to get the optimal result.
Okay, okay. And these errors in these delta and epsilon and omega errors are kind of you basically say it's these numbers fluctuate randomly, and then I'm averaging over possible trajectories of this imperfectly controlled system. Is that okay?
Yeah.
Thank you. Thanks.
Okay. For questions, please raise your hand or comment it on the chat. It's lots of fun to be a chairman on Zoom. I have to admit. Yeah. Comments, questions. You can raise your hand. You can do the question. You can unmute yourself and talk. No. All right. So no more questions. No. Okay. So then. Yeah, I think this is it. Thanks a lot, Yue, for this very nice presentation.
Thank you very much.
And yeah, so I will say let's thank the speaker again, but I think we should clap now. Thanks a lot. Thanks a lot, Yue.
Thank you very much. Yeah.
Good. And let me remind you, if I'm not wrong, I think tomorrow at 12 there's going to be another seminar. Okay.
Right.
So, yeah, I think the host is going to be Geza.
Yes, yes. You should tell me how you host such a thing.
Yeah, I don't know. I just switched it on and it was working.
Okay, great. Good. Okay, then see you tomorrow.
Very good. See you.
Bye.
See you.
Bye.